Module 2, Data Link Layer Protocol. Layer 2 of the Open Systems Interconnection, or OSI model, is called the data link layer. In simplest terms, the data link layer describes the procedures, called protocols, that control data transfer across the physical infrastructure at Layer 1. To control data transfer, protocols at this layer perform two important functions. They establish a link between the sending peer and the receiving peer. Peers are the devices at either end of a point-to-point link, and they reliably transfer data across that link. Data link layer WAN protocols establish point-to-point links, while data link layer LAN protocols provide multi-point connections. In other words, only the two endpoints of a WAN connection, usually two WAN routers, communicate with one another, while all nodes in a LAN can communicate with all other nodes. As mentioned in Module 1, all WAN connections consist of three basic elements: the physical transmission media, electrical signaling specifications for generating, transmitting, and receiving signals through various transmission media, data link layer protocols that provide logical flow control for moving data between peers in the WAN. This course focuses on three technologies that provide the physical layer elements of a WAN connection: dedicated carrier lines, Integrated Services Digital Network, or ISDN, Digital Subscriber Line, or DSL. For each of these WAN connections, a subscriber can choose among several data link layer protocols. Most WAN routers prompt you to choose a data link layer protocol by asking for your method of encapsulation and providing a list of supported data link layer protocols. Encapsulation, in this sense, is the process of wrapping a network layer protocols packet, such as an IP packet, within a data link layer protocols frame. Encapsulating network layer protocols enables their transfer across a point-to-point link. This module discusses two general-purpose data link layer protocols: High-Level Data Link Control, or HDLC, and Point-to-Point Protocol, or PPP. PPP is the default encapsulation for many routers and is discussed in depth in this module. However, much of this discussion is informative. Unless you require changes to PPP's default operation, configuring PPP is mostly automatic. In addition to HDLC and PPP, a number of data link layer protocols, such as Link Access Procedure for D-Channel, or LAPD, Asynchronous Transfer Mode, or ATM, and Frame Relay, can encapsulate WAN traffic. LAPD, ATM, and Frame Relay are discussed in Modules 4, 5, and 6, respectively. In this module, we will describe two protocols that enable you to aggregate lines: Multilink PPP, or MP, and Multilink Frame Relay, or MFR. We will then introduce the concept of tunneling, as well as a tunneling protocol called Generic Routing Encapsulation, or GRE. GRE is a network layer protocol that is generally associated with security in a virtual private network, or VPN. VPNs establish secure communications over public networks such as the Internet and are discussed in depth in Module 7. GRE, however, can also be used in private WANs and in conjunction with data link layer protocols to provide connectivity for legacy network layer protocols, to route multicast traffic through routers that are not configured for multicasting, and to connect LANs that use incompatible IP addresses. HDLC is one of the oldest data link layer protocols for the WAN. In fact, it predates the PC and was originally developed for mainframe environments. Because of this, HDLC was originally designed for use with primary and secondary devices, such as a mainframe with dumb terminals. Although HDLC has been updated for use in the PC environment, you may encounter the following terms which originate from its early use. Normal Response Mode, or NRM. In this mode, a secondary device can transmit only when the primary device specifically instructs it to do so. Asynchronous Response Mode, or ARM. A secondary device can initiate a transmission. However, the primary device controls the establishment and termination of the link. and asynchronous balanced mode, or ABM. Devices at both ends of a connection are configured to be both primary and secondary devices and can establish a link, transmit data without permission, and terminate a link. HDLC uses 3 different types of frames. Unnumbered frames establish a link. Supervisory frames carry error and flow control information. Information frames carry the network layer packets across the WAN link. Although PPP is the name of a single protocol, most often PPP refers to an entire suite of protocols. Most of the PPP suite is shown in this slide. Specific protocols are briefly mentioned in this section to give you an overview of PPP. These protocols are then described in more depth in later sections. Every PPP connection requires the peers to exchange frames from at least 3 protocols, and to exchange them in a particular order. Link Control Protocol, or LCP frames, are exchanged first. One type of Network Control Protocol, or NCP frame, the one appropriate to the data being delivered, is exchanged next. PPP frames are exchanged last. Other than PPP itself, LCP is probably the most important protocol in the PPP suite. LCP frames are used to establish, configure, and maintain the link between peers. After LCP establishes a link, peers must exchange NCP frames. NCPs carry information about how to control or manage other protocols, primarily network layer protocols. The network layer protocol used by the information in the PPP frame determines which type of NCP frames must be exchanged. For example, if the PPP frames are carrying IP packets, then IP Control Protocol or IPCP frames must be exchanged before the PPP frames can be sent. PPP frames carry the actual information being transferred over the link from the upper layers of the OSI model. In PPP terminology, this information is called a datagram. The remaining protocols in the PPP suite, all of which are optional, include the following. Encryption Control Protocol, or ECP, is an NCP that can configure options for encrypting PPP datagrams. Link Quality Reporting, or LQR, is a link configuration protocol that monitors how many frames are being dropped on the link. All authentication protocols provide different ways to authenticate passwords on links configured to require passwords. As the figure will show, a PPP session is divided into phases during which the various protocols may exchange frames. A PPP session proceeds in the following way. During the link dead phase, the physical layer is unavailable and there is no activity. If a peer wants to begin a session, it signals the physical layer and waits for the physical layer to indicate that it is now up. The session then enters the link establishment phase. Peers exchange LCP frames during the link establishment phase. If the peers successfully establish a link, the session enters the authentication phase. During the authentication phase, peers exchange authentication protocol frames. Although authentication is optional, the session passes through this phase whether or not authentication was chosen. If the sending peer authenticates successfully, or if no authentication is necessary, the session then enters the network layer protocol phase. During the network layer protocol phase, peers exchange NCP frames and PPP frames. More than one protocol per session can be used during this phase. For example, peers might exchange IPCP frames, then send PPP frames with IP datagrams, then exchange AppleTalk Control Protocol or ATCP frames, then send PPP frames with AppleTalk datagrams, and so on. During the link termination phase, peers exchange LCP link termination frames. The session is then terminated and returns to the link dead phase. You can configure WAN routers or other devices to use optional protocols in the PPP suite. In addition, many protocols in the PPP suite, such as LCP, allow you to manually configure options. To choose a setting for an option, you may need to know a value assigned to the setting. For example, one of the authentication protocols discussed later in this module, the Challenge Handshake Authentication Protocol, or CHAP, allows you to choose among several authentication algorithms. To use the algorithm called MSCHAP, you may need to know it has been assigned the value of 128, although it is more likely that the router software developers will provide a text option from which to choose. All values associated with PPP are controlled by the Internet Assigned Numbers Authority, or IANA, and are updated at www.iana.org/assignments/ppp-numbers. When one of the peers in a PPP session has been configured to use protocols or options that are not used by default, the peers negotiate these options. They do so by exchanging configuration frames for the protocol in question. This slide shows a simplification of this frame exchange process. Most of the protocols in the PPP suite include the following or similar types of configuration frames. Configure request. The configure request frame contains information about desired changes to the default configurations. Configure ACK. If a peer that receives a configure request recognizes and accepts all of the optional configurations, it returns a configure ACK. Configure NACK. If the peer recognizes all optional configurations but refuses any or all of them, it returns a configure NACK. The configure NACK frame includes information about which options are refused and which values of that option the receiving peer is unable to accept. Configure reject. When a peer receives a configure request that contains either unrecognizable configuration options or options that are non-negotiable, it returns a configure reject. LCP frames are encapsulated in the information field of the PPP frame. LCP has a set of configuration options, and two PPP peers will use the default settings for these options unless one peer signals a request to change the default configuration. To request such a change, the peer sends an LCP configure request frame, and this frame type is specified in the LCP code field. The information about the configuration change is included in the LCP data field, which can contain information about multiple LCP configuration options. Configuration options that are not included in the configure request frame remain at their default settings. We will now discuss LCP configuration options. When configuring a link, the peers must agree on how much data can be contained in the information field of PPP frames. The value that communicates this frame size is called the maximum receive unit, or MRU. The default value of the MRU is 1500 octets. To increase or decrease this value, the sending peer uses the maximum receive unit configuration option. The quality protocol option indicates whether or not peers will use the link quality report, or LQR protocol. LQR monitors the quality of a link by determining how much data is being dropped. The use of magic numbers enables the detection of looped-back links. When a link is looped back, frames are returned to the sending peer. Magic numbers are random numbers that the sending peer assigns to its frames. When the receiving peer replies, it augments the magic number in the reply frames. The sending peer can then detect the difference between sent frames and received frames. By default, peers insert a 0 where a magic number would otherwise be inserted. If you use LCP echo request, echo reply, and discard request frames to test a link, enabling the magic number option is useful. Also, if you choose to enable LQR, you must enable the magic number option. The protocol field compression option allows peers to compress the information in the protocol field of PPP frames from the default 2 bytes to 1 byte. The IANA assigns a protocol field value for each protocol. Typically, this value is less than 256. Because 1 byte is capable of representing the values 0 through 255, most protocol fields can be easily compressed to 1 byte. Enabling the address and control field compression option allows peers to compress address and control fields in the PPP frames. These fields have static values and thus are compressed easily. The authentication protocol option turns authentication on and enables you to choose among the 3 authentication protocols available in the PPP suite. These authentication protocols are described in the next section. Authentication for the PPP suite is what most people think of as password protection. In other words, the user must provide a password to set up the PPP link. The PPP protocol suite includes 3 authentication protocols: Password Authentication Protocol, or PAP, Challenge Handshake Authentication Protocol, or CHAP, and Extensible Authentication Protocol, or EAP. For this discussion, the peer that requires authentication is called the authenticator. The peer that wants to establish a link with the authenticator is called simply the peer. For example, when you connect to the Internet from a home computer, your modem or broadband router is the peer. Your Internet service provider's router requires a password and is the authenticator. PAP is the simplest possible authentication scheme. The peer is provided a password, and the authenticator knows what that password is. The peer sends its password to the authenticator. The authenticator acknowledges the password, and the link is established. Passwords in PAP pass directly over the wire. Anyone capable of tapping into the wire can obtain the password. CHAP solves this security problem by using the following process. The authenticator challenges the peer. The peer combines its password with a string of text and then performs a calculation called hashing on the resulting string. Hashing results in an encryption or hash value that the peer sends to the authenticator. The authenticator knows both the agreed-upon string of text and the peer's password. The authenticator performs the same hashing calculation and compares its hash value to the hash value it received from the peer. If the hash values match, the authenticator acknowledges the authentication, and the authenticator and the peer can proceed with the link. If the hash values do not match, the authenticator continues to issue challenges until the peer returns a matching hash value or runs out of retry attempts. CHAP is more secure than PAP, but it is not the most secure authentication protocol available today. EAP makes it possible for PPP to use authentication schemes that are not part of its own protocol suite. For example, the authenticator and the peer might use the authentication scheme defined by a network operating system. In this case, LCP frames specify using EAP. EAP frames negotiate the type of authentication that will be used, and EAP encapsulates frames from other authentication protocols. Although EAP enables you to use authentication schemes, it is not actually an authentication protocol. PPP supports NCPs for many network layer protocols, including IP, IPX, AppleTalk, and Systems Network Architecture, or SNA. Each protocol in the NCP family has a unique set of configuration options. These options specify parameters required by the protocol that NCP is managing. For example, IPCP includes configuration options that communicate important IP addresses, such as the IP addresses for the primary and secondary domain name services, or DNS servers, to the receiving peer before frames are sent. Most of the other network layer NCPs include a configuration option that serves a similar purpose. IPCP also includes an IP compression protocol configuration option, which indicates a request to compress the IP datagram in the PPP frames. Most of the other network layer NCPs include configuration options that similarly indicate requests to compress their respective network layer protocol packets encapsulated in the PPP frames. For more information about IPCP and other network layer protocol configuration options, see www.iana.org/assignments/PPP-numbers. The PPP suite includes a protocol that enables data compression across the link, Compression Control Protocol, or CCP. The CCP configuration options enable you to specify which type of data compression algorithm is applied to the datagrams. CCP can support nearly any compression algorithm. The IANA has already assigned numbers to many of these compression algorithms, including those listed here. Developers of compression algorithms can apply to have the IANA assign a number to their algorithm. Some developers may not need to get an IANA assigned number. Organizations that have purchased an Organization Unique Identifier, or OUI, from the Institute of Electrical and Electronic Engineers, or IEEE, can use their OUIs to identify proprietary blocks of code, including compression algorithms and encryption keys. An OUI must be purchased by any organization that assigns MAC addresses to hardware. The OUI is the first 24 bits in a MAC address. CCP includes the option to identify compression algorithms by an OUI. The PPP suite includes a protocol that enables data encryption across the link. Encryption Control Protocol, or ECP. To encrypt text, devices that support ECP apply a mathematical algorithm to the text, and this algorithm changes the text into nonsense. The algorithm includes an assigned variable known as the key. Only devices with the appropriate key can decrypt the encrypted text. The configuration options in ECP enable you to specify which type of encryption algorithm to apply to the datagrams. Like CCP, ECP includes the option to use proprietary encryption methods which are indicated by their association with OUIs. The IANA has also assigned values to standard encryption methods, such as the Data Encryption Standard, or DES, and the Triple Data Encryption Standard, or Triple DES. DES and Triple DES are described in Module 7. PPP and other data link layer protocols, such as frame relay, establish a single point-to-point connection, which may not provide sufficient bandwidth to meet a business's requirements. Link aggregation protocols address this limitation. Theoretically, link aggregation is a simple idea. Effectively double your available bandwidth by using 2 physical cables to connect your endpoints instead of only 1. Triple your bandwidth by using 3 cables. Quadruple your bandwidth by using 4 cables, and so on. For example, you could aggregate 2 T1 connections of 1.544 megabits per second each into a virtual single network connection with an underlying bandwidth of 3.088 megabits per second. However, to take advantage of multiple physical cables, data link layer protocols must be modified to fragment frames into smaller frames that can be passed simultaneously over separate cables and then reassembled by the receiving peer. Link aggregation protocols, including multilink PPP and multilink frame relay, MP and MFR, do exactly that. The following sections describe MP as well as 2 protocols that can be used with MP: Bandwidth Allocation Protocol, or BAP, and Bandwidth Allocation Control Protocol, or BACP. As its name suggests, MP is an extension to PPP. There are only 2 differences between regular PPP and MP. MP introduces 3 additional configuration options for LCP, and an MP header is added to the information field in the PPP frame format. In this section, we will discuss the additional LCP configuration options: the maximum receive reconstructed unit, the short sequence number, endpoint discriminator options. The maximum receive reconstructed unit, or MRRU configuration option, provides 2 important functions. First, the inclusion of the MRRU in an LCP configure request frame indicates that the sending peer wants to use MP. If the receiving peer acknowledges the option, it must assume that all of the frames received on different cables from the same peer should be processed as part of the same point-to-point link. The MRRU is required if a peer wants to use MP. The MRRU also replaces the MRU, the maximum receive unit. The MRU specifies the size of the frame that can be sent over a link. The MRRU specifies the frame size once all fragments are reassembled. The default for the MRRU, like that for the MRU, is 1500 octets. The sequence number assigns an order to frame fragments so that they can be reassembled properly. The MP header can have a long sequence number or a short one. A short sequence number is 12 bits and enables a frame to be split into a little less than 5,000 fragments. The 24-bit long sequence number provides enough bits to create more than 16 million fragments. Unless you are bundling a large number of cables together, the short sequence number is probably sufficient. The long sequence number is the default, so if a peer wants to use the short number, it must request this option. When using MP, the receiving peer gets frame fragments from different cables. It must therefore be able to distinguish between multiple sending peers. The receiving peer can distinguish between sending peers using one of the following methods: authentication, an endpoint discriminator, manual configuration. Using the normal PPP authentication option enables one peer to recognize fragments from the same authenticated peer. On links where authentication is not required, the endpoint discriminator option can be used instead. The endpoint discriminator enables a peer to distinguish frames from sending peers based on one of the following: a locally assigned network address, an IP address, a MAC address, a PPP magic number, or a telephone number. Authentication and an endpoint discriminator can also be used together to provide a more secure method of distinguishing between peers. In a situation where a dedicated bundle is set up between endpoints, the links can be manually configured to accept all frames from the bundle as if they are coming from the same peer. A bundle is a group of aggregated links. Bandwidth Allocation Protocol, BAP, is a link management protocol that can be used with MP to improve the management of multiple links. BAP configures, maintains, or terminates individual links in a bundle. MP can be used without BAP, but when using MP alone, peers do not coordinate the adding and dropping of individual links. Like PPP, MP uses LCP to set up the initial link and to terminate the final one. Without BAP, however, peers can add or drop individual links indiscriminately. If a peer tries to send frames over a link that another peer has dropped, those frames are dropped. Using BAP requires adding another configuration option to LCP, the link discriminator option. Negotiation of this option is required. It allows each link in a bundle to be numbered so that BAP can keep track of the individual links. Keep in mind that BAP doesn't replace LCP. LCP frames must still be used to configure the first link during the link configuration phase. This includes configuring MRRU and other options added by MP, the link discriminator option required by BAP, and the authentication of other LCP options available to basic PPP. When BAP is being used, peers must exchange the following frames: LCP frames that contain both the MRRU configuration option and a link discriminator option, BACP frames to configure options for BAP, BAP frames to configure the multiple links being used, NCP frames for the appropriate Layer 3 protocol, and MP frames. BACP is explained in a later section. BAP configurations are required in some types of frames, but are optional in others. To understand when configuration options are required, you must understand BAP frame types. Request frames are described here. Each BAP request frame has a corresponding response frame as shown in the slide. Link configuration frames. A peer sends a call request frame to request that a new link be added. A peer can also send a callback request, which requests that the other peer add the link by calling back on that link. Link maintenance frames. Every time a link is added using either a call request or a callback request, a call status indication frame must be sent to verify whether or not the new link was successfully added. Link termination frames. If a peer determines that a link in a bundle is no longer needed, it can send a link drop query request. Unlike LCP terminate requests, which must always be acknowledged, link drop query requests can be refused. If a link drop query request is acceptable, the peer sends an LCP frame to terminate that particular link. The table in this slide summarizes which BAP configuration options are required and which are optional in different types of BAP frames. Link type option. The link type option specifies the speed and the type of link. Peers are required to include the link type option in call request and callback request frames. In call or callback response frames, peers are allowed, but not required, to include the link type information. Phone delta option. The phone delta option provides either an actual phone number or some other unique identifier for the port to which a link is connected. Peers must include this number in callback request and call response frames and are allowed to use this number in a call status indication frame. No phone number option. The no phone number option informs the receiving peer that the sending peer already has its phone number. A call request frame can include the no phone number option. If this option is included in the call request frame, peers must not include the phone delta option in the call response frame. Link discriminator option. The link discrimination option designates which link the peer wants to drop and refers to the link discriminator number that was set up by the LCP. This option is required in link drop query request frames. Call status option. The call status option is used only in call status indication frames. A value of 0 indicates that a call was successful. Other values can be assigned to indicate why a call failed. The call status option also indicates whether or not a peer should retry adding a link. Reason option. The reason option contains an ASCII text string that describes the reason for a request or response. Peers can include the reason option in any BAP configuration frame. BACP is an NCP that manages configuration options for BAP. Before peers can exchange BAP frames, they must exchange BACP frames to negotiate which peer will be favored in the event of a race. That is, when peers attempt to transmit BAP requests simultaneously, one of the peers' requests must be favored. The favored peer's BAP request frame will be used. BACP accomplishes this through the use of configure request frames that contain the favored peer configuration option. Each peer is assigned a magic number. The peer with the lower number becomes the favored peer. To review magic numbers, refer back to the Link Control Protocol Configuration Options slide in this module. Asynchronous transfer mode, or ATM, arose out of the effort to establish transmission, switching, signaling, and control techniques that would enable an intelligent fiber-based network. To deliver new services such as video conferencing and video on demand, as well as to provide more bandwidth for the ever-increasing volume of traditional data, the telecommunications standardization sector of the International Telecommunication Union, or ITUT, introduced ATM, a technology that provides a common format for services with different bandwidth requirements. ATM combines the benefits of circuit switching, which include predictability, short delay, and guaranteed capacity, with those of packet switching, which include flexibility and efficiency for intermittent traffic. These characteristics of ATM enable the high-speed transfer of voice, video, images, graphics, and data through public and private networks. ATM has been widely adopted because of its unmatched flexibility. It supports the broadest array of technologies, including DSL, IP, Gigabit Ethernet, frame relay, synchronous digital hierarchy, or SDH, and synchronous optical network, or SONET, E1, E3, T1, T3, and wireless platforms, to name a few. Current implementations of ATM support data transfer rates of 1.5 to 9,953 megabits per second, so the same technology that can be employed in a LAN or campus backbone may also be employed in the infrastructure of the wide area public telecommunications network. ATM standards will be discussed in more detail at the end of this section. To achieve the desired benefits, ATM combines the following features: fixed-size cells, connection-oriented service, and asynchronous multiplexing. Fixed-size cells. ATM transfers information in 53-byte units called cells. ATM cells contain only basic path information, which allows switching devices to route the cells quickly. ATM's fixed length also simplifies the transmission and reception of data. It is much faster to process a known packet size than to discern the start and end of variable length packets. In addition, the small ATM packet ensures that voice and video can be inserted into the stream often enough for real-time transmission. Connection-oriented service. ATM also provides a connection-oriented service, which means a logical connection between two ATM endpoints must be in place before information is exchanged. Because connection state information is maintained, data also arrives in the proper sequence, and quality of service or QoS parameters such as transmit delays and average throughput are guaranteed. Asynchronous multiplexing. Asynchronous multiplexing allows ATM to be more efficient than synchronous technologies such as time division multiplexing or TDM. TDM cannot support bursty data, even during periods of voice silence, because bandwidth is statically allocated. Because ATM is asynchronous, time slots are available on demand. ATM is the world's most widely deployed backbone technology. This section focuses on ATM as it is used to provide digital subscriber line or DSL WAN connections made through the public carrier network. DSL was developed with the idea that ATM would be used for the broadband network. This fact, coupled with the superior breadth of services and applications with which ATM interfaces, has served to make ATM the data link layer used on most, if not all, DSL links, and especially on asynchronous digital subscriber line or ADSL links. ADSL and ATM are ideal for Internet access. In this figure, the DSLAM connects directly to a broadband ATM switch, which is connected to a broadband access server. The access server connects to a core Internet router and authenticates users accessing the Internet through the broadband access network. To separate the analog voice from the ADSL data, a plain old telephone service or POTS splitter is installed at both the customer's premises and the public carrier's CO. For more information on ATM and DSL connections, see Module 5, DSL WAN connections. A basic ATM network consists of a set of ATM switches and network adapters interconnected by point-to-point ATM links or interfaces. The ATM switch is responsible for cell transmit through the ATM network. On an ATM network, each attached device has immediate exclusive access to the switch. The cell size is small enough that latency is reduced when multiple streams of traffic reach the switch at the same time. ATM switches support two primary interfaces. The user-to-network interface, or UNI, connects ATM endpoints to an ATM switch. The network-to-network interface, or NNI, connects two ATM switches. As the slide shows, UNIs and NNIs can be further subdivided into public and private UNIs and NNIs depending on whether the switch is owned and located at the customer's premises or publicly owned and operated by the telephone company. An additional specification, the Broadband Intercarrier Interface, or BICI, connects two public switches from different public network providers or carriers. ATM networks are fundamentally connection-oriented, which means that a logical connection must be set up across the ATM network prior to any data transfer. When this connection is set up, there is only one possible path for cells to take, so they cannot be received in the wrong order. ATM setup standards define two types of ATM connections. The virtual path, or VP, identified by a virtual path identifier, or VPI, and the virtual channel, or VC, identified by the VPI and a virtual channel identifier, or VCI. VPIs and VCIs are established during the connection setup phase. These values are carried in the headers of ATM cells to facilitate switching. Virtual channel. A VC connects two ATM endpoints and is the basic unit of switching in an ATM network. VCs are established for the duration of the connection only. Virtual path. A VP is established between switches, that is, across an NNI, to transport large numbers of virtual channels. A VP bundles VCs with the same endpoints, all of which are switched transparently across the ATM network on the basis of their common VPI. All VCIs and VPIs have only local significance across a particular link and are remapped as appropriate at each switch. By means of VCs and VPs, the virtual connections used to route ATM cells can be set up permanently or on demand. In a permanent virtual circuit, or PVC, the connection between endpoints is direct and permanent. In this way, a PVC is similar to a leased line. The advantages of PVCs include the guaranteed connection and the fact that call setup procedures are not required between switches. Disadvantages include static connectivity and manual setup. In a switched virtual circuit, or SVC, the connection is created and released dynamically whenever an endpoint needs to send data. Because the connection stays up only as long as data is being transferred, an SVC is similar to a telephone call. Unlike PVCs, SVCs do not require manual setup and only consume network capacity when they are established. SVCs are set up automatically through signaling. The disadvantages of SVCs include the extra time and overhead required to set up a connection. Although not a focus of this section, ATM also offers connectionless service, which is similar to switched multi-megabit data service, or SMDS. As mentioned earlier, ATM cells are switched based on the VPI and VCI in each cell's header. Cells do not have an endpoint address in their headers, but rather these identifiers which change from switch to switch before arriving at the endpoint. As the slide shows, a cell that is sent from a telecommuter's office would be routed as follows. First, the WAN router addresses the cell with VPI2 and VCI9 and sends it out. The cell arrives at port A on ATM switch A. Switch A consults its routing table and changes the VPI and VCI to 5 and 7 respectively. It then sends the cell out on port B as per its routing table. The cell arrives at port C on ATM switch B. Switch B consults its routing table and changes the VPI and VCI to 4 and 8 respectively. It then sends the cell out on port D as per its routing table. The ATM reference model is a three-dimensional model consisting of 3 planes and 4 layers. ATM planes. The 3 planes which span all layers include the control plane, which generates and manages signaling requests for call setup and teardown, the user plane, which manages the transfer of data across the network, and the management plane, which maintains the network and carries out operational functions. Its subdivisions manage the different layers and planes. Physical layer. The ATM physical layer handles medium-specific functions, such as bit timing, medium characteristics, and physical connectors, as well as transmission functions, such as framing and signaling. ATM layer. The ATM layer is primarily responsible for the generation of the cell header and the functions associated with the header, including the switching and routing of cells, flow control, congestion notification, bit error detection in the header, and cell delineation. AAL. The ATM adaptation layer, or AAL, is the interface between the higher layer protocols and the ATM layer. When relaying information it receives from the higher layers, the AAL segments the data into ATM cells. When relaying information it receives from the ATM layer, the AAL reassembles the payload into a format the higher layers can understand. ATM adaptation layers. Different classes of AAL have been defined to support different types of traffic or services. The most popular adaptation layer, AAL5, is used for IP and WAN applications. The HP ProCurve Secure Router supports AAL5. When a packet initially enters the ATM network, it is segmented into ATM cells. Each cell consists of 53 octets or bytes. The first 5 bytes contain cell header information, and the remaining 48 contain the payload or user information. UNI and NNI cells have a slightly different header format. NNI cells have no generic flow control or GFC field. Instead, the first 4 bits of the cell are used by an expanded 12-bit VPI field. This allows for larger trunks between public ATM switches. In addition to the VPI and 16-bit VCI fields, ATM cells contain the following header fields. The 4-bit GFC field provides local functions such as flow control from endpoint equipment to the ATM switch. This field is presently not used. The 3-bit payload type, or PT field, indicates in the first bit whether the cell contains user data or control data. If the cell contains user data, the second bit indicates congestion, and the third bit indicates whether the cell is the last in a series that represents a single AAL5 frame. If the cell contains control data, the second and third bits indicate maintenance or management flow information. The 1-bit cell loss priority, or CLP field, indicates whether the cell should be discarded if it encounters extreme congestion. Finally, the 8-bit header error control, or HEC field, detects and corrects bit errors. UNI cells also use this field for cell delineation. Operation, administration, and maintenance, or OAM ATM cells are sent over a reserved VCI to constantly monitor an ATM link. 5 hierarchically separate levels comprise the OAM functions of an ATM-based network. The HP ProCurve Secure Router uses F5 OAM cell loopback generation to verify that the ATM link is open from end to end. Configuring F5 OAM for an ATM subinterface sets the standards for how often the link is tested and what qualifies the link as up or down. For example, you can configure the retry up count, which determines the number of consecutive end-to-end F5 OAM loopback cell responses that must be received before the ProCurve Secure Router changes a PVC connection state to up. You can also configure the retry down count. When the interface misses receiving this number of consecutive end-to-end responses to its requests, the ProCurve Secure Router changes the PVC connection state to down. Finally, you can configure the retry frequency. This setting determines the frequency in seconds at which the ProCurve Secure Router transmits F5 OAM loopback cells when verifying a PVC state change. The benefits of ATM are rapidly extending from the local loop into the core network. As carriers blend ATM with other technologies, ATM over SONET SDH and DSL over ATM, for example, and standards continue to develop, ATM is becoming interoperable with virtually every technology in the network. End-to-end service standards. The most basic ATM standards are those that provide the end-to-end service definitions. User interface standards. ATM UNI standards specify how a user connects to the ATM network to access services. Standards exist for T1E1, T3E3, OC3, and OC12. OC48 is in progress. Network connectivity standards. 2 ATM networking standards provide connectivity between network switches and between networks. BICI and Public Network-to-Network Interface, or PNNI. The more feature-rich of the two, PNNI, supports service-sensitive routing and bandwidth reservation with scalability to large networks. Cell standards. All ATM traffic is carried in cells, but applications do not use cells, so specific ways of putting the data into cells are defined to enable the receiver to reconstruct the original traffic. These include RFC 1483, which specifies how inter-router traffic is encapsulated into ATM using ATM AAL5. LAN emulation, or LAN, makes an ATM network look and behave like an Ethernet or token ring LAN. Multi-protocol over ATM, or MPOA, classical IP over ATM, and voice and video adaptation schemes that have been developed to use the highly efficient AAL1 for traffic that has no natural breaks, such as a circuit carrying bits at a fixed rate. For a list of all specifications that the ATM Forum has completed and approved, visit the MFA Forum at the link presented on this slide. A tunnel is a virtual point-to-point link across a multi-point access network, such as the Internet. In a sense, a tunnel emulates a WAN link. Most data link layer protocols that are used in WAN connections encapsulate other protocols and set up a point-to-point link. Tunnels can provide these same two services over the Internet or in an extranet. They can also be used in a private WAN if some traffic is incompatible with intermediate routers. Using tunnels over the Internet or in an extranet usually requires additional security to protect the data being exchanged. These additional security requirements are discussed in Module 7. This section focuses on how tunnels can be used to route incompatible traffic through intermediate routers. When incompatible traffic is encapsulated in a tunnel, that traffic travels unnoticed by routers other than those at the endpoints of the tunnel. A tunnel also creates a routing system that hides addresses from the intermediate routers, which is useful if you need this level of security. 3 tunneling protocols are briefly introduced here. Generic Routing Encapsulation, or GRE. Point-to-Point Tunneling Protocol, or PPTP. Layer 2 Tunneling Protocol, or L2TP. GRE can encapsulate multiple network layer, data link layer, or multicast protocols into an IP packet. GRE then uses source routing to create a virtual point-to-point link through an IP network such as the Internet. GRE is described more fully in the next section. PPTP is a proprietary tunneling protocol created by Microsoft. It encapsulates PPP and creates a tunnel for a PPP frame to travel through an IP network. In the PPTP tunneling system, PPP handles the encapsulation of network layer or multicast traffic. L2TP is an Internet Engineering Task Force or IETF standard based on PPTP and the proprietary Layer 2 forwarding or L2F protocol created by Cisco Systems. Like PPTP, L2TP relies on PPP for encapsulation and then routes PPP through an IP network. The main difference between L2TP and PPTP is that L2TP can use IP security or IPsec for authentication and encryption, while PPTP uses proprietary or PPP-based authentication and encryption. IPsec will be discussed in detail in Module 7. GRE can transmit a variety of protocols over an IP network. GRE uses the same protocol identifiers that Ethernet uses and can encapsulate any protocol Ethernet can. GRE encapsulates other protocols' packets within GRE packets, which in turn are encapsulated within IP packets. This section briefly describes several situations, other than security situations, where GRE can be useful. Legacy protocol connectivity. In a network that is still using network layer protocols such as AppleTalk, Microsoft's NetBIOS, or IPX, GRE can be used to route these protocols through the WAN, even if intermediate routers don't support them or aren't configured to route them. With GRE, such protocols can also be routed across the Internet. Multicast routing. Multicast routing can be set up at the network layer or the data link layer. Within a single LAN, a data link layer protocol such as Ethernet can easily handle multicast traffic. However, when WAN traffic is combined with traffic from multiple LANs, multicast routing protocols, which operate at Layer 3, are more robust. Distance Vector Multicast Routing Protocol, or DVMRP, and Multicast Open Shortest Path First, or MOSPF, are examples of multicast routing protocols. Configuring protocols such as DVMRP and MOSPF at every router can be time-consuming and inconvenient. Using GRE to hide multicast protocols from intermediate routers can make such configuration unnecessary. Incompatible IP address connectivity. If a corporation merges two LANs that have incompatible IP addresses, it can use GRE to route between those LANs, without manually changing IP addresses at multiple stations. Although PPTP is a tunneling protocol, it was designed to provide users with secure dial-up access to their Internet service provider, creating a VPN. As a result, it supports both encryption and authentication. The two devices establishing a PPTP tunnel use PPP to create the initial connection. They then use a TCP session to exchange control and management information, and use the PPP connection to establish a tunnel. With PPTP, the control connection is maintained separately from the tunnel. As the slide shows, PPTP uses GRE to encapsulate PPP data packets. It also adds an IP header and a media header. The media header defines how the packet is transmitted. For example, the packet could be transported over PPP, frame relay, or Ethernet. To secure the data being transmitted across the tunnel, PPTP can use Microsoft Point-to-Point Encryption, or MPPE, or PPP's native encryption algorithms. PPTP also supports PPP's authentication mechanisms such as PAP, CHAP, and EAP. Unlike PPTP, L2TP uses the same tunnel to exchange control messages and data packets. Combining the two channels makes it easier for companies to configure their firewall and manage access to their internal networks. Another difference between PPTP and L2TP is L2TP's use of UDP rather than TCP. UDP is considered to be more efficient than TCP, creating less overhead. The two devices establishing an L2TP tunnel exchange control messages to create the tunnel. Once this tunnel is established, the sending device encapsulates each packet in PPP and then in L2TP. Next, the sending device adds a UDP header and an IP header. Finally, the sending device adds the media header. As mentioned earlier, L2TP supports IPsec for security. In this module, you learned about the following: HDLC and its configuration options, the PPP suite and the configuration options associated with specific protocols within the suite, the phases of a PPP session, the purpose of link aggregation protocols and the configuration options associated with MP, and the purpose of tunneling protocols such as GRE, PPTP, and L2TP.